first of all, it is a pleasure to be here. I really have enjoyed the previous sessions and to learn a little bit about ILSI, including its kind of balancing of interests and goals and context to really have an effective and credible kind of context for these meetings and your research. I'm going to give a very overview idea of some of the excitement of quote unquote big data, and then some cautionary tales that big data themselves are not the solution to anything without care. I'm going to leave out a lot, many of your favorite things possibly. I'm going to leave out completely formulae, whatever word you'd like to use for that, and just try to generate some interest in discussion. So here we go. Here's an outline. I don't usually read it because if I do, then I will spend my whole time on that. But I will say that with the transportation bill having been passed, that maybe some paving of the road is at least now conceptually and financially possible. So the drumbeat, the big data drumbeat, the popular media, these are things that were in an editorial that Marie Davidian and I wrote in Science Magazine a few months ago. And likewise, the New York Times and other places have had a lot of big data splashes. It's going to drive our future. It's going to translate genomic information into cancer therapies and so on and so forth. I'm not going to read all of this, but just give you a feel. There are vast amounts of data being generated, whether it be in nutrition science or brain science, and we've seen some examples of that, and I'll put up another picture that will look a lot like the ones that were put up. This data, and I will say maybe also information, and that's going to be one of my points, that big data don't necessarily imply big information. They're central to decision making. The New York Times said, good with numbers, fascinated by data, the sound you hear is opportunity knocking. All of this is job security for statisticians, computer scientists, informaticians, so on and so forth. So what's the old world small data? Well, I, again, am listing snippets, but in-person interviews, phone interviews, hard copy data forms, questionnaires, basic laboratory detectors, scintillators, whatever else it might be, and lots of other things. I mean, the new world is all of those things, plus web forms, transaction records, social networks, phone and email records, Facebook friends. We could add LinkedIn also, road toll records, believe it or not, border crossings, gene chips, so on, so forth, and so on. Some of it being very passive, some of it being active, some of it being overt, some of it being covert. And so the tsunami of data is increasing, and part of the issue is it's got to be captured if we're ever going to use it. I mean, the National Security Agency apparently has to sort of do catch and release things all the time in terms of never storing all of those telephone things, but trying to have artificial intelligence that can say, yeah, let's grab this snippet because it said something, or at least had a phrase they thought was interesting. So some of those data could produce a social network. This one having to do with contacts in phone records and so on, but quite frankly, a similar kind of topology might be used for a gene network, might come out to be an electronic grid. The point here is that we have lots of data. This picture already has taken a mass of data and organized it at least into a picture. And the more statistical mathematical issues are, well, how is this picture possibly different from other pictures that might be similar to it? How can we, in addition to the nice eye candy graphics, how can we quantify some things and compare? And that's a challenge that's been around ever since data were generated, but becomes even more challenging in the current world. Here are more data sources. Not going to read them all again, but just trying to set this frame that it used to be controllable in some sense, and at least as researchers and as policymakers kind of knew where to go to get it, and now you may not even know where to go to get it, but it's going to get you, and a lot of it has lurking information and context, and some of it may not. Google flu is an example I'll put up in a minute. Here's another brain scan kind of trace, and the reason I'm putting this up is this comes from a sleep study, and the point isn't so much what the curves represent, their electrical activity, but what do you want to say about this? What are the goals here? These are scans from different people over different time periods, so on and so forth. And so there are statistical techniques now, and I'm afraid to know where to go to do the pointer because I'm probably going to change everything, so I think I won't bother. the kind of things we do and others do with this is to say, can we partition these traces into what is more of a grown-up version of principal components, principal curves. So we can talk about, if you'd like, a population curve, and then an individual variation curve around that. And these curves may have a principal mode of variation and a secondary mode. And by doing this kind of onion peeling, be able to get to the point where you have a quantity that you can get both your head around and statistical analyses around to start quantifying and therefore comparing. And I'm not giving the technology here, but just sort of the issues. Here's an example from Google Flu. Google Flu takes search words that have to do with things like aspirin and this and that and the other things, and try to come up with a prediction about flu epidemics, both in a spatial sense and in a time sense. And this is just one trace for the nation. And it turns out there have been studies that show that they can beat the CDC in terms of predicting and have very few false positives. And so here we have an example where it's completely uncontrolled in the sense that we aren't designing an experiment, but that the behavioral aspects of using Google to search, along with some mining of those data, have allowed one to come up with what looked like pretty good predictions in advance of at least the CDC's timing on creating and putting out their publications, and quite frankly, getting the reports from physicians, drugstores, and so on. So, road construction and maintenance. I put at the top, although I'll save it till later when I'm doing something with it, the design of experiments and observational studies. And the word design will be a big theme in what I'm saying. Data collection, obviously. Storage and husbandry. With the tsunami, how do you store it? And if you store it, how do you have anybody, including yourself, know where to go to find what you've stored? Analysis and reporting. So what was the old world data storage? Well, it was relatively expensive, and it was heavy, too. It was things like files and file cabinets. Maybe in the early days of computing, physical tape and big disks, both physically big and heavy. The new world is relatively low cost. That doesn't mean it's inexpensive. Well, I don't know. Is there any way for somebody to tell me where the pointer is on this? The red button. It is the red button. Of course, well, anyway, you can't see it anyway, so it doesn't matter. Storage media have large capacity that are relatively small with fast read and writes, low in price, but it turns out in one of these theorems of computing, the price per pound has actually remained approximately constant. The devices have become lighter, the prices have gone up and so on, but the price per pound has stayed about the same. Just as with a highway, demand exceeds capacity. As soon as you have the ability both to generate and store more data, it seems to immediately get full. And so the issue of how to deal with these data, or if to deal with these data, are really prominent. More. Make sure I don't do it. Wonderful. I had one of these, and in my last trip, it got confiscated by TSA.
I probably got it.
Yeah. And I tried to convince them that the only danger for these was if I were outside the airplane, but they didn't seem to believe it. So I haven't gotten another one yet. Anyway, data husbandry and informatics. I mean, part of the issue that is challenging, having nothing to do with the technical statistical aspects, is making sure that as we store these data in whatever context, that we have common definitions so that we can combine information across data sets, that we have informative metadata. And I think probably the area, maybe I should add neuroscience, and you can tell me, Miguel, whether I should, but the area that I think has been a leader in this is genomics, with very good annotation, structured posting of data in a way that essentially everybody who's doing analysis on gene signatures know exactly where to go to get what and what the what means. And that, I think, is developing in other areas too. But without that, you have data morgues as opposed to anything else. Of course, data sharing is important, both in terms of access controls and disclosure protection, but also hopefully a culture of openness within the range of possible openness. Data analysis techniques have burgeoned and blossomed. Some of them are algorithmic and always have been. What I mean by that is you write a computer program, data go in, something comes out. Some of them are model informed, meaning that they are algorithmic and aren't really into like a formal statistical likelihood. I'm not explaining what that means, but sort of basic statistical principles were underlying them. Some of them are model-based, literal, the binomial likelihood or whatever. Basically, I'm quite agnostic about how one generates a procedure. I'm not so agnostic about making sure that we evaluate the properties of the procedure. So creativity is necessary in this large data context. Support vector machines and other such things are needed, but we need to make sure to evaluate statistical and other operational properties no matter how the procedure, how the program got written. So here are some golden oldies, and if you've had any statistical course at all, hopefully you've had something about t-tests and confidence intervals. There are others going down the line that are a little more modern, including jackknifing, bootstrapping, Bayesian methods, and so on, at least modern in the sense of being used prominently. And they're still very important. In fact, the underlying principles of principal curves come by being a more general version of Fourier series. There are lots of new wave things. I'm not talking about them in a technical way, but almost just trying to give you a feel for the length of the list as opposed to anything else. Causal analysis is a big field now having to do with trying to take observational data and at least some aspects of experimental data that aren't protected by randomization and try to make sure to get from association to causation. Data mining, knowledge discovery, all those wonderful words. The lasso, we try to have words now that are a little bit cool so that people think that we might actually be interesting at cocktail parties, and we're becoming more interesting at cocktail parties, I think. All of these things trying to both move away from very constrained modeling approaches that require the normal distribution to be holding, and also to deal with some of these very complex data structures. So again, not going to give a lecture on any of these, but just listing some. You may have your favorite that's not there. So Miguel, here's a neuroscience example. The kind of data tsunami here has to do with just lots of, instead of pixels, which are two-dimensional things, voxels, which are three-dimensional objects at whatever resolution the scanner happens to be able to produce. They're arranged spatially, obviously, in the brain, and they're also temporal in the sense of you may have studies over time, and they're also hierarchical in that you may have several people and different aspects within a person. And so here's an example, and I'm not giving the details, where we're trying to predict certain transmission areas in the brain, and see if I can lean forward. The modeling for this was done with something called random forests. It's not a model-based technique, but it's something that tries to, in a very real way, let the data tell you what's going on and produce complex interaction structures that are essentially impossible to think about with traditional models, but come out by building complex trees of relationships and then combining evidence over those trees. The point being, taking a very complex data set, hopefully identifying a goal, that's always a good idea, and then improving, in this case, some pretty modern technology to come up with what is at least a color map of what regions are lighting up for various aspects in this study. That's sort of the upbeat part. And I'll get back to upbeat, I hope, also. But then I have to be a statistician in a sense with a little bit of a cautionary tale, which is at least part of our culture. So this snippet is from the New York Times big data set of articles or discussion. It has its perils. Huge data sets and fine-grained measurement. There's an increased risk of false discoveries. You have this opportunity to look around at all sorts of things, and you may come up with incredible significance, and we'll get back to this in a couple of minutes, but Trevor Hastie at Stanford has said that when you're kind of looking through a massive haystack of data, many bits of straw can look like needles. That's not a new concept, but it actually is sort of blown up many orders of magnitude by having so many more opportunities to discover something. The good news is we're developing procedures that allow one to at least try to calibrate the operation of those searchings and getting at least some idea of how likely it is that you got something good. The other comment has to do much more with the opportunity for purposeful statistical shenanigans as opposed to, if you'd like, you might think of this as malpractice and this as mispractice, but the opportunities are great. They've always been around, but they're even greater than they used to be. So care is needed. Big data I don't know whether to say does or do. We'll decide whether big data is kind of a concept or is a collection of plural objects. Does not imply big information or relevant information. Hopefully in many cases it does, but it doesn't automatically do so. And so at least for science, we need to require uncovering causal relations, and big data has produced many predictions and associations and some causal relations, but we have to go from discovery and association to causation. Predictions don't necessarily need that. The Google flu thing can work well without necessarily having understood some mechanistic property, but at least for most of science, we want to have causation as well as association. So no amount of statistical creativity can rescue a poorly designed study or a poor instrumentation, whether the design be a purposeful one or just the design is the data are coming in and I have to deal with them. So validity and success depend on statistical and domain-specific knowledge. It's not in any sense that statisticians have a monopoly here, but at least hopefully we are part of a team that puts together approaches, both designs and analyses that are worthwhile. So I'm giving very toy examples of these things, but it's one of my favorites because I couldn't figure out how to do it myself. In terms of subject area knowledge, it's not big data. In fact, it's n equals 2 data points. So you're looking at either wind direction or the spin directions on molecules or anything else like that where it's a compass direction. And the reported values are 10 degrees and 350 degrees, and somebody asked you to give you the typical value. Well, is it south? Is it the average of 10 and 350? Or indeed, do you get smart and say, well, 350 is like minus 10, and that it's north? Now, this may look trivial, but think about trying to kind of make a general approach to this, or at least feeding these numbers into a computer and not telling it anything about what they are. You have a 50-50 chance at least of making a mistake, I think. So again, a toy example to push the idea that there's nothing in fancy statistical things that will replace subject area knowledge. Random sampling and random allocation. These are really the mainstay of the scientific method. In observational studies, we can't always get that, but it would be nice to have it as a goal that we give up reluctantly and frequently because the practical aspects don't allow us to have it. Now, there's been a comment in Congress that random sampling is not scientific. I'll leave that off to the side. I'd like to talk with the new version of Daniel Webster and convince him that in fact it is, but in fact it is the mainstay. And indeed, sampling can produce amazing, at least for me still, precision from relatively small samples. National surveys using just a couple of thousand people properly stratified can get an honest, if you'd like, plus or minus 3 percentage point error on opinions, and you can have similar sorts of successes, if you'd like, in general. The whole idea of random sampling and random allocation, when you can do it, is that at least in a statistical sense, it produces independence between assignment to treatment, and I don't necessarily mean medical treatment, but whatever the it might be, and the attributes of individual units. So you really have a chance to do a causal association in that there's no kind of selection that has to do with the good people going someplace and the not so good having to go on to the other. George Box said, and has said many times, if you want to see what happens when you perturb a system, you must perturb it. That would speak against being able to use observational data to understand things. And we all know that that's not literally true, but he's really saying care is needed. Lincoln Moses, who is deceased, was a statistician at Stanford, behaved like Lincoln and looked in every way you could imagine like Moses. I mean, he looked like he came down from the mount every day to go to the office. It's possible to learn from experience, but doing so is fraught with difficulties. And I think that's kind of the place we are with big data and with most of our studies. So in the spirit of this care is needed thing, I'm going to give just a few examples of the importance of what I'll call really our traditional values, and maybe some that are neo-traditional, that the big data world doesn't necessarily obviate the need for the usual kind of principles. And one that may be not usually listed first or listed ever, and I'm giving it label 0, is level 0 design. So it's all the importance of design. I have been involved with and reviewed many studies where the thing that caused the study to fail is that the team wasn't constituted properly, that it was a study of electromagnetic force effects on the ecology, and an engineering firm did the study because it was electromagnetic waves, and there really wasn't a statistician or an ecologist or anybody in any semi-leadership role, and you're just fated to disaster. There's no question about it. Similar for not having proper resourcing. So for me, level 0 design is a sociological aspect, and that is constitute teams to at least have a good chance of success. And then level 1 and beyond is, in some sense, the usual things. Good design for efficient use of resources, certainly to address ethical considerations, for example, by monitoring a clinical trial, to either eliminate or allow adjustment for things like batch effects, lab effects, technician effects, and other things where we don't get, and I'll be getting to that in a minute, complete confounding of things, to assure that goals are achievable so that we don't get to the research equivalent of Russell Dodge's down east thing and which way to east Melanotic. Come to think of it, you can't get there from here. And there are many studies where late in the game you can find out that no matter how fancy your instrumentation, no matter how big your sample size, you just didn't have a design that would allow you to answer the question you actually wanted to answer. So in terms of efficiency, I'm going to go over this very quickly, in fact, almost not at all. But to give an idea of sitting back and thinking hard about the design issues, imagine you're trying to, in fact, this came up because there was actually a balance scale in Miguel's talk too, at least up in some upper portion of your slide. You're trying to measure the weight of 8 unknown masses, and it's a power of 2, so this makes it easy for myself. And you could take, and you want to do it to the precision that would be the equivalent of 8 separate measurements on each of these masses, where you put it on one side of the beam and load up the weights to get on the other, or think of a more sophisticated machine with a similar thing. You could weigh each one 8 times, and you'll get this variability, if you'd like, for the mean for each, so that's 64 weighings. But if you sit back and think a little bit, you can use that balance being to do much more of a general kind of balancing by allocating weights to different sides. And here's just an example of one design. The first row says put all of the weights on one side and then the unknowns, and then put whatever you need to on the right-hand side to get the balance. That gives you the total. And then all these other ones are just contrasts amongst the weights that are orthogonal and informative. And with a very simple statistical model, these 8 weighings give you the statistical precision equivalent of having done all 64. You get sigma squared over 8 for each. Again, a little toy example, but the kind of thing to, especially if the machine is expensive to use, either in cost or time, can pay big benefits. The importance of the sampling plan. There's always a sampling plan, even for big data, but we may not know what it is. In purposefully designed experiments, we know what it is, whether those be randomized or observational, because we say we're going to follow the following kind of people or objects, whatever they may be. Certainly the ones that are kind of gold standard are these random and stratified and cluster and snowball. There are haphazard, convenient and series, and there's I have no idea. And in a lot of situations with big data especially, but actually in the past too, you don't know what the sampling plan is, but the thing to keep in mind, and I try to push in classes and in collaborations, is there's always a sampling plan that relates what you've seen to some population, but if you don't know the plan, you won't actually know what population your results refer to. And so it's not enough to say, I have sampling plans in the studies that I purposefully designed. There's always one. It's the data getting to you is the sampling plan, and the issue is, do you know what it is, or can you accommodate issues that are produced by the unknown sampling plan? So I could give examples from weight loss studies, and decided that you've probably seen so many of those, and David Allison, I'm sure, gave you several, and so I won't. But here are some from lung function. These are from studies that I was involved with in the 6 City study at Harvard, many in the mid-70s and early 80s. This is a case of probability of getting a good spirometric reading in a subsequent visit after having measurements on the person for a current visit. And the x-axis is actually deviation from your predicted lung function. So it's a 0 would mean you're right on the mark for your age and gender, and a plus would be you're better off, and so on and so forth. Smokers are less likely to produce a good blow the next time than non-smokers, and if you're at deficit relative to your peer group, now you're less likely to perform well the next time. And without having a good blow, you get at least missing data in the context of the criteria that are there. So informative missingness. It's not just a random sample of people that end up giving the data for the next visit. Here's another example. You've all seen ones like this. Again, I'll use lung function. Here's one that's the other way around, the healthy participant effect or the healthy worker effect. Lung function decline in later life begins to accelerate and goes down until eventually there's no lung function, and then you know what's happened. But in most studies, you get dropouts, and at least in this case, generally the dropouts are for the people that are more compromised, not always. And so if you don't have a way to do a statistical analysis, and there are some that can protect you from that, if you do a naive analysis, you'll get a curve that looks like this. And you'll be much more optimistic, if you'd like, about the lung function preservation than you might be. In a weight loss study, as we all know, you can either have dropouts for people doing well or dropouts for people doing poorly, and the action of those two can depend on whether it's early in the study, late in the study, and so on. All of these things are, if you'd like, the sampling plan. Missing data are a manifestation of a sampling plan, and without some understanding of it or protection from it, you can make mistakes, big mistakes. Here's another one having to do with selection effects. And it's a golden oldie, but it's still one of the best. And this is a study of 5-year mortality for an old study looking at well, called the Coronary Drug Project, looking at cofibrate as a prevention of death. And so these are the data that were put up, and at least, in fact, in the presentation when this study was revealed, it was put up just like this. Look at the dramatic improvement in survival, or the reduction in death rate, by having taken more of your medicine, or at least reported to have taken more of your medicine. And everybody was saying, well, this is a real win for the intervention. Unfortunately, when you add the placebo data in there, you find that it was even better to be an adherent person to placebo. That clearly what's going on here is that there are personal characteristics, lifestyle characteristics, whatever they may be, that are producing the good outcome, and it had nothing to do with this treatment. Now that's an extreme example, if you'd like, but this issue of selection effects for things that are actually predictive of the outcome need to be considered in all studies. Confounding, again, nothing new to all of you, but outcomes can be affected by all sorts of things, the experimental run, the lab tech, and in fact, that lab tech on day 1 versus day 2, the interviewer, clinics, community, whatever. And if you don't have an experimental design that allows you either to automatically control for those things or to adjust for them, you can be in one of those situations of, come to think of it, you can't get there from here. And a classic example of, there have been some gene expression experiments and other things where all of the cancer tissues were done on one day or in one run or on one chip, and all of the normals on another, and you have no idea, at least from the data, really, about whether the association is with the disease status or with the chip status or with the day or the humidity or whatever else it may be. So stratified randomization provides some protection. You don't need to have a perfect design, but you need to have information that can allow you to deconfound things. And so that brings up this more extreme version of confounding, which is called Simpson's paradox, and at least for biomedical researchers, I like to use that you have a treatment that's good for men, good for women, but bad for people. The idea being that, how much time do I have? Is that what that note's about? Okay, do I have 10 more minutes? Is that okay? It's an example of this extreme confounding where there's an association, in this case with gender and outcome, that isn't balanced over the treatment. So I'll give this picture and I'll skip a few things after that. This picture shows that you have a win for A over B if high numbers are good, no matter whether it's for women or men. But if the distribution of men and women is as I've described it in this picture, if you were not to stratify on gender or adjust for gender, you would find just the reverse finding. So the issue being, again, that especially in observational data, you need to try to collect information that, even if you don't care about it for any other reason, can help control for confounding. I'm not going to do this picture because I don't have time. I will do this one. Uncertainty is certainly one of the job descriptions of statisticians and others, but it really is for all of us. We need to estimate it and we need to communicate it. And I push for communicating with every statistical entity some kind of uncertainty, and a few of us have pushed for this kind of reporting to really not only make it easy to look at things in tables, because all of a sudden the standard errors or the confidence limits are out of the way, but to really stress the idea that the estimate is not just this one number, but it is in fact the estimate coupled with its uncertainty connected at the hip, or whatever other phrase you'd like. And again, it's very, I could give a whole lecture on uncertainty, estimation, and communication. I'm not going to, but that we need to not only communicate it, but help people understand how to think about it. Alicia, I guess, had given you something on tolerance limits for fortification, and here's just another example. This, if you'd like, was uncertainty in the traditional sense of the normal distribution mean having a variability. Here's the one that's more model uncertainty. This is from an old carcinogenicity experiment on mice again, where for these data, and the sample size was very big. This was a study trying to look at really low-dose extrapolation by 50,000 rodents being treated with 2-AAF at various doses. And you find that several of these low-dose curves fit the data as well as any other. You could not distinguish between them, and yet have orders of magnitude difference in the virtual safe dose, or if you want to translate this to fortification to something else. And so you either need data on some more data on some other aspect, scientific understanding, or what happens a lot is just default options to say, well, we don't really know, so we're going to do the linear or something like that. The point being, model uncertainty in many of these applications, and I think in many of yours, is as important, conceivably more important than model-based uncertainty, especially if you have a large sample size. The standard errors will be very small, and the only thing that matters is the model doing something reasonable. Okay, I'm going to leave out that. This is, again, this thing about false discoveries. One of the things that big data have done, both in genomics and other areas, is forced us, not just statisticians but others, to get away from the pure form goal of we want to control the probability of any error if the null hypothesis is globally true. We want to make sure that we make no mistakes at all. When you're looking at 3 million genes, or 3 million SNPs, let's say, you will pretty much never be able to find anything out with that. And so what has happened is, and it's not really new, but it's nicely new in the sense of become more accessible and actually been developed a little more, is something now called the false discovery rate, which says we're not going to try to control all of these errors, but we want the prevalence of false positives amongst the positives to be low, which is in a sense really what you'd like. Now the reason it's not really new is it's exactly the same thing as the predictive positives in standard old-fashioned diagnostic testing, but it's become the way to liberate, if you'd like, looking at big data and getting something out of it that doesn't require you to control the p-value to be 0 before you say anything. Here's an example of that using the false discovery rate, and all I'll say is that these horizontal lines have to do with adjustment for multiplicity to control the FDR, but still be able to sort of identify some peaks that are not just the artifact of having searched amongst millions of things. Apologize for having to leave a few things out, but I think I will. So what is statistics? R.A. Fisher, a good place to start with almost anything, in 1948 at the founding of the International Biometrics Society, said biometry, at least, is the active pursuit of biological knowledge by quantitative methods. And Marie and I pick up and quote a few other people, and we're not trying to take a monopoly on this, that it's learning from data and hopefully learning in a way that's purposeful and effective. There are sociological imperatives, and I'm finishing up very quickly. Nothing is purely statistical, but most of science and policy have statistical aspects. Not all, but most. We share responsibility for all of this. This is part of the level 0 design. We have to be there at the beginning, we meaning all of us, I think. We statisticians need to understand the domain-specific context, and at least collaborators have to understand not math stat, but stat concepts, I think is the way to put it. We need to invite and encourage participation in the statistical angle. We need to avoid what I heard one colleague say, to avoid the idea that only historians are allowed to reminisce. I mean, we all should be allowed, at least at a dinner party, to reminisce, and we should all be allowed to have statistical ideas and nutritional ideas, so on and so forth. Education's imperative, and I think not just for the current cohort of all of us, but especially for the data-informed future, and with big data coming, even more than in the past, people need to understand statistical concepts for self-defense, if nothing else. And there's a wonderful book that's now in its 3rd edition. Its 1st edition was in the mid-'80s when Vic Cohen was at Harvard on a Boesky Fellowship. So you see, even Boesky can do some good things. He wrote what he thought was going to be a pamphlet that he would put in briefing rooms for reporters that were interviewing scientists. And it ended up being quite a substantial book. And in the 3rd edition, with he's deceased, his daughter has taken over and so on. It's just a wonderful book for everybody, whether you be a reporter, a scientist, certainly a high school student, and so on. And I highly, highly recommend that. These are exciting times. Big data have vast potential for generating knowledge and improving public policy. However, space-age techniques, all those cool things I listed without telling you about, will not rescue Stone Age data. And big data can be Stone Age. So we have to be a little bit careful. Marie and I try to make sure our guild gets some promotion here, that embedding statistics in science and policy will pave the route to a data-informed future, and statisticians must lead, or I should say, co-lead this charge. And I'll let you go to lunch, but I'll put up one of my favorite pictures from the Tidal Basin a few years ago at the Blossom Festival, and this guy is roaming around. I don't know what he was doing, but I took a picture of him. So.